Hello, and welcome to Beyond the Gates. I'm Annette Kirkland, and this season we're going to be talking about today, tomorrow, always. This season we will highlight how ERDC is delivering impactful solutions today, driving innovation for tomorrow, and prioritizing people always. From groundbreaking research to enduring partnerships, we explore the power of progress rooted in purpose. Today, we're going to be talking about locking in the future, ERDC's role on the Ohio River, and I'm going to be speaking with Gary Bell. He's a research civil engineer, and Allen Hammack. He's a research mechanical engineer with the Coastal Hydraulics Laboratory, otherwise known as CHL. Good morning, gentlemen.
Good morning.
Good morning.
Good morning. So we're going to start off with my favorite question. Tell me about yourselves, your background, and your roles at ERDC.
Yeah, good morning. Thank you, Annette. So my background is in physical scaled hydraulic modeling. I'm actually from North Mississippi, a small town called Senatobia. I've been with CHL for about 10 years now. And yeah, that's pretty much the sum of that.
Okay. Oh, come on. There's got to be more. There's got to be more.
Oh, there's always more. We'll get into that later.
Okay, great. Okay, Alan?
Yes, I'm Allen Hammack. I'm a mechanical engineer at the Coastal Hydraulics Lab. I do all kind of things related to hydraulic structures and emphasis on navigation locks. Degrees in mechanical engineering from Mississippi State, master's in undergrad, and also began work at ERDC in 2007.
Okay. Y'all have to work closely together with State and Ole Miss. How does that work?
It doesn't.
I was going to say surprisingly good.
Okay.
Like I said, it doesn't work well at all.
No, that's just funny. Okay. All right. Well, we're going to just dive right on in here too. I understand we are assisting with the redesigning multiple locks on the Ohio River. Why these particular locks, and why is it so important to upgrade them now?
So everything the Corps of Engineers does is based on emergency status and benefit cost ratio. So they look at the economic impact of everything that we touch, and they determine if the benefit of some sort of action, some way of spending money, what we're spending money on, if that is above the cost that of that action, then that project can proceed. Mm-hmm. And that project is done through everything that USACE does. There's also emergencies that happen. Those are some exceptions. But this project or these projects fit the benefit cost ratio. So the Ohio Mississippi River system, the Ohio River empties into the Mississippi River. Those two rivers and all their tributaries is the largest navigable waterway in the United States. The Upper Ohio is a set of 3 locks that we're actually supporting the redesign of, or the design of new locks at those sites. That area has locks that are shorter than other locks on the Mississippi River. They're 600 feet long as opposed to 1,200 feet long. And some of our barge tows, our commercial barge tows that use the locks, that are moving the products that are driving the commerce on the waterway, they are longer than 600 feet. So when they get to the locks, they have to separate into typically two pieces to get through the locks, which takes time. Mm-hmm. So, and the locks that are there, they don't operate as efficiently as we can of our newer locks because of their age. They're on the order of 80 to 100 years old at this point. So they require maintenance and other things. Now we can operate them more efficiently. So these 3 locks have been targeted as a need by the Corps of Engineers, the big Corps, not ERDC, but the mm-hmm. Corps of Engineers at large in Washington. And we are supporting new locks at all those sites to speed up navigation, make it more reliable, make it safer, all of those things.
Okay.
Go into why these 3 locks.
Okay. And with infrastructure just aging so much around the world, it's just easy to understand why these things need to happen. So, Gary, do you have anything to add?
No, I think Alan pretty much summed it up really nicely.
Okay, great. So the Ohio River doesn't just move goods for businesses. How does this project help with national security?
So it's kind of a hedge answer, but the businesses support the economy.
Right.
The economy is national security. a way you don't have to attack our infrastructure and our people to attack our country. You can attack our economy.
Right.
And ways you can do that is to negatively impact our economy, harm our economy. And that's why we do all this. That's why the Corps of Engineers, which is an Army function, why it is involved at all with navigation. Navigation is one of the 12 national security interests that the Corps of Engineers, or that the Army is interested in. It seems like it's not a military issue, but it is about the stability of our country.
Okay.
And if we destabilize our country, that is absolutely a national
correct.
interest, a national security interest.
Absolutely. Gary, do you have anything to add?
No, once again, Alan.
You're agreeing with Alan.
I'm agreeing.
Okay, awesome. Okay, so we are going to dive into the next question. The team at ERDC is testing a new way to fill and empty the locks. What does that look like? How does that work? And give me some behind the scenes.
So every lock site, you're going to have to figure out what you want the lock to look like, and there's a process for figuring out what filling and emptying system design. That's part of the hydraulics, which is based on some of the navigation, the traffic, some of the economic concerns, economic situation for this lock. There are also structural concerns, mechanical concerns, all the different disciplines, the scientific disciplines and engineering disciplines you can think of. That they're probably some part of all of this. And then, so the district, or the USACE district that is sponsoring this, they will start with some of that information, start making some of those decisions. Then they'll come to, and depending on how you want to evaluate it, how you can design it, and how well it's understood, how it's going to perform, then you may decide to do some sort of modeling work. And that's where we provide technical support at ERDC. We provide technical support on the design, and we also provide support on the modeling side of it. So not just design guidance, but how does this site-specific model, how is this going to perform in the real world? So we provide a lot of that modeling support, whether it be numerical or physical modeling. Navigation locks tend to end up being at a physical modeling stage. You do numerical modeling, but there's also physical modeling because we are required to for certain design types. So that's something that we do. We help determine what the model needs to look like in consort with the sponsors, and then we determine our plan, and then we will testing plan. Then we will build the model. Everything is done inside the fence line at ERDC. It's custom made, even all the way from the structural setup, building the model, and then all the electronics, then the testing of it, and then the analysis of the answers or of the results, and then making recommendations for what the design needs to be. We do all of that, and there's a big team at ERDC, not just.
We have some world-class modelers, do we not?
Yes.
Awesome.
And it starts with the people who build the models.
Right.
And that's, Gary does more of that than I do, but we have teams that's all they do is build our models. So we want to put a focus on them, how well they work at our DPW, our model shop, machine shop, our welding shop, all of those. We can't do the modeling without them. So we're going to build those models, and then we're going to test them, and then we are going to provide analysis and recommendations to the sponsors. And sponsors don't deal a lot with all of that part of it. They hand it off to us, and we kind of just take care of it.
So behind the scenes, how long does it typically take?
For depending on a lock study, a year and a half to 2 years, something like that.
To build the model?
To build and test the model.
Right.
So the building itself, 4 to 6 months, something like that. But the overall project could be a year and a half to 2. That's kind of typical.
That's a lot.
That's a lot. Our costs seem high. Don't really. So maybe $1.5 million to $2 million.
Right.
But the design and construction effort overall for a new lock is going to be in excess of $1 billion. So it's a lot of work. It's a lot of money to do the modeling. But compared to what the prototype is going to be, it's very small.
And if anyone has ever seen these models, they're so, how do you say it, so particular about everything about them that it's understandable that it takes so long to make it perfect the way it needs to be to mimic what it needs to mimic. So, all right, so we're in models. Models are super cool, as we're talking about, and important. So, fun fact, physical river models are how Waterways Experiment Station got its start. So there's that. So I understand the team created a scaled-down model of the lock system to run tests on new designs for the structure, as we're talking about, as well as navigation models. What are the differences between using a physical model and a computer model? Is one better than the other?
Yeah, that's a great question. And I think this has been a good discussion leading up to this question to
Right.
kind of walk us through it. So that is a fun fact. For those that don't know, Waterways Experiment Station got its start from the flood of 1927, one of the most devastating natural disasters in America's history. Waterways Experiment Station was founded in Vicksburg after that to better understand the Mississippi River system and the flooding that occurs at certain events. And so that kind of got the start, and we actually built the world's largest physical model, I think, still to this day.
Right.
Located in Clinton,
Clinton,
Mississippi.
absolutely.
You know, and a lot
We've
of
actually
people-
done a show about that model.
That's right, and it's pretty impressive. So that kind of started our foundation at ERDC, right, and everything built up off of that. So the difference between a physical and a computer model, that's a really good question. I think the best way to answer this, I tried to explain to my 5-year-old son what I do one time. And I brought him to my work, and all he could see is pushing the red button that turns the pump on. So he just thinks that's all I do,
That's how you
is
push
the
a button.
and turn the water on, and we get our answers. But I guess the best way to explain that is, they're both good tools depending on how you use them and what your problem is. So probably, for Alan and I and other engineers at ERDC, one of the biggest challenges we have is we get these problems that are not your typical standard problems, right? These are tough water resources, questions that we have to answer, and we have to decide what the best tool is to answer that, right?
Right.
To get the data, and there's a lot of things that go into that, whether, it's like the resources available, how much money is available, all these different things that we have to come up with a plan of attack. Alan kind of hit on some of that earlier. And luckily at ERDC, and you hit on it too, Annette, we have a group of some, really world-renowned researchers and engineers and scientists and technicians and, everybody. We have a team, very diverse team that we get together, and we'll sit in a war room, if you will, and we'll hash it out, and we'll decide, hey, what can we do? What's the best options for this? And we have different individuals with different subject matter expertise from different, areas of science, the science community, and we'll all get together and we'll determine that. When we say the word model, we've all heard it. What does that mean? Whether you're talking about physical or numerical. The way I break it down in my mind, and I'm a little simple, I guess, but I think.
Well, that's one of the reasons we've done this show is for people to plain language understand what goes on.
Sure. No. So when we're thinking about a model, as a modeler, my goal would be to limit my assumptions of that model, and what that means is the unknown variables, the things that we have to kind of normalize to try to get results to a believable state, if you will. And a lot of that depends on the modeler's background and experience in running the model and basically interpreting the model data, right? So the difference between physical modeling and numerical modeling, if you build the physical model correct, as you hit on in it, our level of precision is ultra high, and it makes it, sometimes painful, because we're getting it within, millimeters of accuracy in terms of the geometry and everything else. So, that could be a little difficult, but it really goes a long way, because what the physical model tells you, you see it. If you see scour, if you see an eddy, if you see a hydraulic jump, if you see a problem, then it's there,
Right.
and that's one of the benefits of that. Now, computer models or numerical models, I'll say, also have good benefits too, but again, it's probably more, Alan, you might chime into, but it's probably more it leans on the expertise of the modeler a little bit more, because a numerical model, you can't see the water, you can't see the structure, you can't see the scour, you can't see the rock move, all these things. So you have to have a great understanding of the code, the numerical equations that are running that model, and interpret that data. So that's a really long way to say it depends, and we go through a lot of discussion to determine the best tool to answer these problems as they come across.
Well, what's the hashtag? Water is tricky.
It's very tricky.
And y'all find that out more and more, I'm sure.
We do. And I'll just to piggyback off what Alan was starting to hit on with our, with BPW and the things, and so for what ERDC does and what makes us unique, again, is that we have that collaborative relationship with our DPW. We're able to, these things that we're building and testing aren't, just a pier, a circular pier or something, which they're very complex. And a lot of times what it requires is some innovative methodologies put into place to get the best possible model built. So, like
I understand sometimes they write it on a napkin.
I hear it all the time. Actually, and I hate to say this, we're actually trying to get away from that in a way that we have we always, and Alan's probably one of our better, if not best, 3D CAD drawers, if you will, but we want to have everything in drawing, but we can't, sometimes something happens, the real world happens, right? A design change happens, an emergency happens, a failure happens. And we have to make it happen, like that in our model, and then we write it on a napkin.
Well, I have a notepad beside my bed. If I might wake up in the middle of the night and think about, this would be super cool. So you gotta take it when you have it.
Exactly.
And if this would work. Oh, hey, what do I got? I got a napkin.
Exactly.
So sometimes you get inspired to fix something without realizing your subconscious is going into overdrive sometimes to figure out stuff. 100%. I know mine is.
100%.
Awesome.
Yeah, I want to add something about the physical model versus the numerical model. It's important to know inherently one is not better than the other.
Right.
Overall.
Right.
And for some applications, physical models are better. In other applications, numerical models are better. We don't tend to do one or the other. We try to do them together.
Right.
So that they can inform one another. There is certainly value in doing both of them. If we probably half of our lab or more does numerical modeling, and that's what they do.
Right.
It is vital, and very informative. It kind of fills some of the holes of the physical modeling, and also physical modeling fills some of the holes from the numerical modeling. So
ERDC is data driven.
Yeah, that they all work together, and especially for the locks. The locks tend to be what are called USACE mega projects, and as the name indicates, they are very important, very visible, very high dollar studies,
right.
Or construction efforts. It's bigger than what the ERDC does, but we tend to do numerical and physical modeling. You do numerical modeling first because it tends to be less expensive and faster to look at some of the earlier designs and say, hey, this design doesn't work. We don't need to proceed with it. So for a lower cost, we can determine a bad design. And
right.
Also a good design, we proceed with the good design to get, as we move into higher order, more complicated numerical models, and then to physical models. So everything is working together. So this is one better than the other? That is a loaded question. So they are.
Well, does the egg come before the chicken, or the chicken before the egg?
Well, you could go back and so if you go back in time, you think about before computers,
right,
people got better, right,
and
we had computers filling up the space of an entire room, right?
Right.
And now they're so compact, we can do so much more with them. So that development has helped us use numerical models in a lot more, right? But
right.
I guess the key is, and you were hitting on it, Alan, is that if we don't have the data in the literature to help understand the problem, right, to help back up the code, then we can't model it numerically with a high degree of confidence. That's the key. And some things, like Alan was saying, there's applications that numerical models are fantastic for, their strengths and weaknesses if you don't need to build a physical model.
Right.
However, if you have really complex geometry, or if there's something that hasn't been built yet, which is the case of a lot of these lock filling and emptying studies.
Because they're not the same.
Exactly. You have no data, right? So that's typically why we build physical models of those systems. So
right.
We didn't answer your question at all. And then,
yes, you did.
I'll add something he said about what a model is. Everything you learn in math class, science class, all those come together. All the engineering stuff, they're all models.
Right.
Okay. They're all physical model, numerical model. The equations you do, they are models. Every one of them. Model is a very general term. And it's important to know also, every model to some degree is wrong. Every single one of them.
Well, that's disheartening.
Some of the models, the results of them are useful.
Right.
But every
It's
model,
helpful for them to be wrong, right?
well, what I mean by that is they're not going to be exactly right. We're making assumptions, or some of the inputs that we have to them, we may have that a little bit wrong. So this is how engineering and science works. It's not
perfect.
It's not inherently that anybody's doing a bad job.
Right.
It is impossible to get exactly right. We have our interpretation of what we think is going on, and that's how we set up our models. But what if our interpretation is wrong? Okay, what if what we measured, it's not just this number, it's a number within a certain confidence interval, and now we're starting to get into some of the really complicated parts, which makes engineering and science a bit of a challenge.
Right.
So all of those things go in and say, we're going to say this is the answer, or we think this is the answer within this level of confidence, and then we add a factor of safety onto it to make sure that it's safe for operation. I'm quoting somebody, I don't remember who made the quote, but all models are wrong. Some of them are useful.
Okay. Well, that's good to know too. So now, I understand one goal is to make the locks faster and more efficient, but at the same time, they must remain safe. How do you balance efficiency and safety?
So we have, one of the reasons we do all the modeling that we do is to ensure that we have safety. We have design guidance that is developed over decades, and most of those lessons, or the guidance in those and the steps in the design guidance, are based on hard-won information, and we try to prevent those from happening. One of the things I say all the time, I'm sure Gary has heard me say this, all science is inherently, we hold science in high esteem in our society. All science is doing something and watching what happens and writing it down. That's all it is.
Okay.
When you get really down to the essence of it, that's all science is. So over time, we learn things. We learn things that work, and we learn things that don't work. We avoid the things that don't work, and we do the things that work.
Right.
Now, come back to your question. How do we balance efficiency and safety? We have design guidance that has been developed over these hard-won lessons. So we know, hey, build it in these size constraints, and you're going to have pretty good performance. So the usage districts will take that design guidance and come up with a design, and then we will evaluate it. Sometimes with a physical model, navigation models we build tend to be two types of physical models. One is a navigation approach model, which is how the barge tow or a ship would enter from the river, would enter the lock, and then a lock filling and emptying system model where it's how the lock itself operates. So we would do those two sorts of studies so we can make sure that it is safe to operate, but it actually functions properly.
Right.
So we have design guidance that say if it operates within these parameters, you're going to have good performance. But it is also not just do this, 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 and this, and you're going to have a safe lock. It's still, we have to look at this as experienced professionals and say, this is how the model is performing. What does that mean for how the prototype or how the real world lock would perform, how the real world ship would perform? So we do a lot of evaluations like that. We bring the sponsors in, we explain what we saw, what the numbers are, what the not number, the qualitative performance is, and we talk about all of that, and then we make our decisions. The numbers and the data inform our decisions, but they don't dictate our decisions.
Okay.
So we do a lot of work to balance the efficiency and safety of the locks. There's much bigger than just science and engineering interests. There's navigation industry interests. There are national security interests. There is economic interest. That's not just the private sector. It is also federal government interest in keeping our economy moving reliably and safely.
Okay. Well, good to know. So the testing The system now can save time and money down the road. How does your research help catch problems before construction begins?
That's a great question. So, in this case, we're talking about physical modeling, and, we have the model in front of us. Typically, what we'll start doing, and I can't tell you how many times this has happened in my career, where, we begin testing on the model, we'll see something that we didn't expect to see, and it's almost every time, and that's one of those things that you catch it after you start running the model, and you're like, oh, we didn't expect this to happen, or this was something unplanned. So it's just one of those benefits of a physical model in terms of things happen that you just don't plan for, no matter, you just can't. But the ways that we're able to catch these problems is, we'll test the model, obviously, and we have several different ways, different data collection techniques that we deploy. A lot of times, believe it or not, it's just dye and visualization in the flow. We'll shoot dye and we'll see things that we know are going to be problematic, whether we're talking about scour or large eddies or vibrations in the structured gate or anything like along these matters. There's things that happen in the model that we can capture and say, oh, we need to do something about this. Now, this is where, if you have a physical model, you can kind of go in and, I'm going to say this term loosely, but you can play with the model in a way. And what I mean by that is, say, we can put something that diverts the flow, whether it be just a 2x4 on the model itself, and you can say, well, what does this do? What does that do? And then that's where it gets fun for me. I'm almost kind of like a kid in the way that, you start trying different things out and see it, like Alan said earlier, what are the changes? You do something, what changed, and you write it down, and these help capture problems. Now, in terms of lock systems, there's a lot of guidance out there. There's a lot of different, everything's pretty much laid out in front of us in terms of what we're looking for, right? And some of these things are, Hauser forces within the lock chamber itself as your rate. And all that really means is if there's a vessel in the chamber and it's filling and emptying, what does it feel? How much of this bathtub effect do you have going on that's really, there's a limit that's a problem, and you don't obviously want it hitting the walls and things like that. There's other things too, how long does it take? We're talking about efficiency. But for us, we go in and we can implement design changes pretty quickly. Again, I'm going to bring our team with DPW back into the discussion, because we'll go to them and say, hey, we see this problem with this model. We need to build this part, this component. We need to change this. We need to cut this off. We need to glue this on. I mean, it's literally sometimes just that simple.
Right.
And we'll work together a plan to make that change, and then we'll retest what happened. Did that make it better? Did that make it worse? And in the model, nothing happens. There's no failures. Nobody gets hurt. In the real world, failures happen. And
right.
that is the benefit right there.
Absolutely.
That we can make those changes. I mean, we're talking about thousands of dollars. We're talking about cheap and quick and what happens versus obviously life-threatening situations potentially.
Right.
So to me, that's the big impact that we have.
Well, I didn't say it at the beginning, but I'll say it now, because a lot of times I say it at the end. Thank you guys for what you do for the nation. So it's so super important. Everybody that's here that we talk to has such a big role. Everyone has a role in doing that. So thank you for what you do.
Thank you.
Appreciate that.
So ERDC is working closely, as we do. We work a lot with partners and customers, and working with the Pittsburgh District and other partners on this. How does that teamwork make the project stronger?
I love that question.
Thank you. I work hard on these questions.
That opens the door to several things I want to talk about. I'm sure Alan does too. We're very transparent in everything we do. And I firmly believe, Alan and I talked about this, that communication is one of the biggest keys in everything we do. And I mean, communicating the model results, communicating the status, communication across the board, whether it's within our own team at ERDC, with the sponsors, with the navigation industry, with the public. And again, that's another thing that I like this. This is another tool to help get what ERDC does out there so that there's understanding and people know, hey, what we're doing here. But back to your question, working with the district and other partners, this project in particular, especially on this Upper Ohio navigation study, we've really developed this great working relationship where we bring in the navigation industry to ERDC, right? And they have an added role that, hey, what do you guys think about this? You know, you're the ones actually navigating up and down these channels, right? You're the ones coming out of these locks. What do you think about this? And we get invaluable input from them to help us with our design. You know, because I hate to say it, you know, Alan and I and others, we're very, what's the right word? Tunnel vision focused in our subject matter areas, right? I just care about the model and the data and making sure the data is good. And, you know, it's not to say that we're blind to everything else, but we don't, you know, we really don't have the capacity to focus on a bunch of other things because of how important this work is and getting this right. We got to make sure what we're doing is correct, right? So we bring in these partners and they'll come in and they'll offer, like I said, invaluable advice on what they feel or what they think might work. And then we could test it in the model and say, hey, that's great, or no, we need to modify this. And then we bring in all other disciplines, right? And then we've talked about being hydraulic engineers, you know, mechanical and civil, but we get everybody else involved, the structural people and everybody at geotech, and say, hey, do we see any problems with this environmental? I mean, it's an entire collaboration, you know, and it's very impactful. It's great stuff.
Teamwork makes the dream work.
Amen.
So another thing to add is the modeling we do at ERDC is not nearly all of the modeling work that's done. The Pittsburgh District, also the Inland Navigation Design Center, they have done a lot of modeling work. They did a lot of the numerical modeling for this project that was performed before some of the physical modeling, and also at, simultaneously with the physical models, so that they tell us what they're seeing, we tell them what we're seeing, and we all kind of come together and say, okay, this is what we believe the truth is, or at least our understanding of the truth. And what we're talking about for the numerical model, what they see and what they're showing from their model, that informs our models. Okay, well then we need to make this kind of change to our model, and they see what we're doing, and they say, oh, okay, well that means how I can change mine, and it all comes together, just like the numerical and physical modeling that's all done within ERDC, or the same kind of thing with the sponsors. We're all really just one big team working on this.
Right, and you learn from every single project, I'm sure.
Absolutely.
Yep.
So today's barges are much bigger and heavier than when these locks were built. How will the new designs handle that?
So there are design standards, sizes. One of the things that you have to understand about a lock is locks are on a waterway. There's not one lock. There's a lock for every dam that you have in a waterway. And so if you have one lock that is significantly wider, for instance, than the other locks, that barges can go through that, a barge tow can go through that block faster, a larger one can, than it can the others. You have to kind of approach it as a system-wide approach, and what our sizes are going to be for our locks. We talked about the length, 600 foot or 1,200 foot, typical on the Mississippi and Ohio River system, and so we have the locks will adjust on length. They won't adjust on width. The barge tows, because the barge tows will tend to stay the same width.
They need to.
They need to. But as we change the sizes, and we have gotten bigger over decades or over a century now, we have to do it, or we do it over time across the entire waterway, because we have the same vessels that have to move throughout major portions or in the entirety of our waterways. So, but as we get bigger, because we are moving bigger, we have channel adjustments, the draft, which is how much of the vessel is below the water line, and it goes to the channel depth. The more draft you have, which means it's the more material, the more goods that you're able to put on a single barge, that tells you how much you want to draft, or how much depth you have to have for your channel. And if you have the depth in the channel, you also have to have that depth in the lock, because the vessel has to move through the channel and in the lock. So we look at all of these things, and I promise you they are very complicated, major decisions that are done. It's done very systemically and very deliberately throughout the entire Corps of Engineers. So we move slowly, but hopefully we move in a very dedicated direction. We kind of have an idea where we want to go, Certainly, our channels have become deeper throughout the throughout time. Over time, on Mississippi River, we've had, I know, 4-foot mandate, the core 4 foot of draft, so the vessels had to be able to. We had to maintain a channel that vessels could navigate to 4 feet, and then it moved to 6 feet, and now it's 9 feet, and we have some waterways that are now moving to 12-foot draft, and we're looking at ways to safely modify our locks and evaluate our locks to make sure that they can handle all that, because as you have more draft, you have more forces that are going on. So we look at all of that to make sure it's safe, and if it's not safe, we look at ways that we can operate our locks or maybe make other sort of structural adjustments to reduce those forces back to where we can get safe operation.
Okay, that's a lot. That's a lot. Okay. So the Ohio River is key for moving goods and military supplies. How does ERDC's work make sure these locks are ready for anything, anytime?
We try to make our designs as resilient as possible. They certainly, we try to have what we know is moving on the waterways, which is not just commercial traffic, it's not just barge tows or ships, it's also recreation traffic, so fishing boats, also yachts, things all move through our locks. Whatever's on our waterways that has locks moves through our locks. So we have to design for all these different things, and we have criteria that we try to reach for all of them. And all of this goes into our modeling efforts. So, how we can be ready for anything, anytime, or we can try to be ready for anything, anytime that we can anticipate.
Right.
If
you don't know what you don't know.
That's right. So this anything, anytime, that's really, really broad.
Right.
And what we're doing has shown to be a challenge over generations.
Right.
And how we're designing these things, how we operate these things. So we learn from those, learn lessons from past experiences, and when we try to anticipate what's coming in the future, and design accordingly. And how do we do this? We try to improve our modeling capabilities, improve our materials, improve our numerical tools. Look at bigger than what we do with just the hydraulic performance of the locks. Look at new materials. Look at new construction techniques. One thing we don't talk about very much, but we have the buzzword is aging infrastructure. Mm-hmm. But how do we have locks and dam infrastructure that's been in service for decades or over a century in many cases, and how do we rehabilitate those? How do we repair them? How do we extend the life of them? And if you haven't seen a lock or a dam, they're very large. Mm-hmm. We have very large waterways, so we need very large infrastructure on those waterways. So we have gears and gates and things that are a gear a 10, 12 foot diameter, and valves that weigh 50,000 pounds. So these things require, when they were originally built, they required special tooling and special facilities, special factories and foundries. And over time, we've kind of moved away from that type of infrastructure that's in the industry, not in what the government controls.
Right.
So new technology is being developed with additive manufacturing, composites research to help us with how to repair our facilities or how to build new, but using different materials, or not requiring all the as much manufacturing infrastructure to retrofit, build new parts that will fit with what we have, but we no longer have to have a factory that's able to do that. We have tools that will build it in a different way, but it will work at least as well, and in a lot of cases will work much better. So some of our other areas of ERDC and also in the Corps of Engineers look at those kind of things and are helping develop those technologies to help with make it ready for anything, anytime.
Okay, well, good to know. So as we close out, looking ahead, are there any key takeaways you'd like our listeners to understand about this project?
Yes. A lot of stuff that you see on our roads, you see in you think about airports and what things move and how we move products around. There is significantly more material, cargo that moves on our waterways. You don't see it until you're near the waterways, and most people don't live near our waterways.
Right.
So when we talk about a lock and a dam, you may think, I don't know where one of those are. I don't know how many of them we have. We have hundreds.
Hundreds?
We have between 100, I'll be kind of general here, between 150 and 250 locks in the United States. And I suspect most people have never seen one of them. They're big investments for our country. They are very much a significant part of our economy. Even if you don't see them, you kind of only hear about them when something goes wrong, but you don't hear about them every day. So that means that suggests that a lot of things are going right with our locks,
Right,
and our dams. So they're there, even though you may not see them. They're kind of moving in the background in areas where people typically don't live.
Yeah, that's exactly right. Now, one thing I'd like to add is, we pretty much hit the nail on the head with everything to do with locks and, these systems and some of the stuff that Alan and I are involved with. But, if there's listeners out there that are curious about other things and ERDC in general, I believe we have tons of reports that are approved for public release. You are free to go out there and read these. I think they're incredible documents, and I think you can get a better understanding of what we do. But we're always looking for the next generation of brightest. And I think we have multiple pathways to contact ERDC and get in touch with the right people to have these discussions. So if this is something that interests you or something you're thinking about, please reach out. We're looking to build.
That's right. That's an awesome way to end. We're looking to build. Okay. Well, thank you, gentlemen. I appreciate you so much for being on the show.
Thank you.
Annette. This is great.
Thank you for listening. Have a wonderful day, and we'll come back at you next week.